So this time we're going to talk about capacitor and capacitance. So this is how capacitors look like. So what is the function of capacitor? So we say capacitors, these are devices that store electrical energy, and then usually capacitors consist of two conductors that carries energy charge. One is positively charged, one is negatively charged, and separated usually by non-conducting materials, or what we call an insulator. Now if we're going to differentiate insulator to conductor, say conductor, electrons are free to move on that kind of material or conducting materials, while insulator is very poor in conducting or letting the electrons flow. So these are the symbols of capacitors. Two parallel vertical lines. These two parallel vertical lines represent conductors or plates, and then these two horizontal lines represent a wire connecting to the conductor. And there's another symbol. You can also use this symbol, one vertical line and then one curved line. So these two lines here, the straight line and the curved line, represent the conductors, and these two horizontal lines, like this one, represents a wire connecting to the conductors. Okay, so again, capacitors are devices that stores electrical energy. So the simplest form of capacitor consists of two parallel conducting plates. One plate is positive and one other plate is negative. So it takes work, which is then stored as potential energy in the electric field that is set up between two plates to place charges on conducting plates of the capacitor. So this is the simplest form of capacitor. It has two parallel plates. One is positively charged, one is negatively charged. Right? And then the distance between these two plates is D, and then there is potential difference between these two plates. At positively charged plate, it has higher potential compared to the negatively charged plate, right? And these are wires connecting to the conductors, and then the area of the plate is A, and then the distance between two plates is D. Okay. One way of charging capacitors is to connect the wires of conducting plates to the opposite terminals of battery. So once positive charge and then negative charge are established on the conductors, we can disconnect the battery to the conducting plates. This one gives a fixed potential difference between conductors. That is, the potential of positively charged plate with respect to the negatively charged plate. So initially, these two plates are neutral. It means the number of protons present in one plate is also the number of electrons present in the same plate. So if this plate has 10 electrons, then it must also have 10 protons. To be neutral, the number of neutrons will also be the number of electrons. Number of protons will be equal to the number of electrons. So as well as this plate is also neutral, so the number of protons there is also the number of electrons present in this plate. Now, how to charge a material? Either you remove electrons from that material or you put electrons to that material. Now, how to remove electrons to the material? With a voltage source, we can remove the electrons from one plate to another plate. So if that material loses electrons, then more protons will be present to that plate. Now if more protons will be present to that plate, so it means that plate is positively charged. Now, the other plate will gain electrons. So if that plate gains electrons, it means more electrons present on that material, on that plate. So meaning, if more electrons present, then it will be a negatively charged plate. More protons present on a material, it means that material is positively charged. And then more electrons present on that material, so it means that material is negatively charged. So let us charge these two plates. One will be negatively charged and the other one will be positively charged. So how to do that? Let us remove electrons. Let us transfer electrons from this plate to the other plate with the voltage source. Usually it's a battery. For small amount of voltage source, we'll use battery. So we're going to push the electrons with the voltage source. Okay, just look at the flow of electrons. All right. So this plate, the upper plate, loses electrons, and those electrons flow in this conducting wire, and then all electrons transfer to this plate. Then this plate has more electrons present, so it means this plate will be a negatively charged, and this plate has more protons because it loses electrons transferred to the other plate. So this plate is now a positively charged, but the whole capacitor is still neutral, right? Because the number of electrons loses by the upper plate is also the number of electrons gained by the lower plate. So we're going to add these two charges. The charge of the upper plate plus the charge of the lower plate still equal to 0. Then we can disconnect these two plates to the voltage source once the charges are established. Okay. Then this voltage source gives a fixed potential difference between two conductors. What do you think will happen if a material gains more electrons? It will be more negatively charged. Now, if the area is fixed, what do you think will happen to the areal charge density of that material? So more electrons will flow, or more electrons will gain by the material, and then the area is fixed, so it means there's also increase of areal charge density. Areal charge density is the charge per unit area. So greater charge at fixed area, then meaning greater charge density. Now, if I'm going to increase the voltage difference between these two plates, we will measure that using the voltmeter. So 0, it means no electron flow. So if I'm going to increase the voltage difference, more electrons will flow. So this plate will be more negatively charged, and this plate will be more positively charged. So as you can see, as you increase the charge or electrons that will flow, there is also increase of charge density or areal charge density. And if you're going to increase the voltage difference between these two plates, look at the electric field, you observe what will happen. Okay, as I increase the voltage difference, more electric field lines. More electric field lines meaning greater electric field. So as I increase the voltage difference between two plates, there's increase of number of electric field lines. So it means there's increase of electric fields. But the ratio of charge per voltage difference, that does not change, right? And that ratio of charge and voltage difference between two plates is what we call capacitance. Okay, look at the capacitance. It's 0.3 picofarad. Farad is the standard unit of capacitance. So no matter how I increase or decrease the voltage difference between two charged plates, there's no change of capacitance, still 0.3 picofarad. So capacitance is defined to be the ratio of amount of charge that is on the capacitor to the potential difference between the plates at this point, right? So that's charge per voltage difference between two plates. That's capacitance. And then unit of capacitance is farad, and 1 farad is equivalent to 1 coulomb charge per volt. Okay, that's capacitance, right? So let us calculate the capacitance of a capacitor. If this capacitor consists of two parallel plates, one is positively charged and one is negatively charged. Right. So suppose this is the two parallel plates. These are two parallel plates. One is positively charged and then one is negatively charged. When we add these two charges, the charge of this plate plus the charge of that plate will be equal to 0. Okay, it's neutral. Alright. And we know, I discussed already what is the electric field between these two plates, two parallel plates, if one plate is positively charged and the other plate is negatively charged. We know that the electric field between these two plates is the areal charge density per over permittivity of free space. Okay, we derive this equation using Gauss's law. Alright, and then the areal charge density is the charge per area. Charge of this, charge of either of these two plates. So charge per area. So I'm going to replace areal charge density by charge over area. The electric field is charge per area per permittivity of free space. And then electric field is, okay, I will replace the charge density, areal charge density by charge per area. Then we have charge per area per permittivity of free space. And we know that if this is plate A, plate B, the voltage difference between plate A and plate B is given by the electric field times the distance between these two plates. So these two plates are separated by distance d. Between these two plates are insulator, or say vacuum, free space. Alright, so this is the voltage difference between these two plates. It's electric field times the distance between them. So I will replace electric field by this equation. Then the voltage difference will be equal to charge per area, charge times distance between two plates over area, permittivity of free space. So this is how you obtain the voltage difference between two parallel plates. If you know the charge, the distance between them, the area, and the permittivity of free space. So, how we have capacitance equals permittivity of free space times area over distance between two plates. From the definition of capacitance, that is the ratio of charge per voltage difference between two plates. And we know the voltage difference between two plates is this one. The charge of either of these two plates times the distance between these two plates, and then over area of one of the plates over permittivity of free space. So I will replace the voltage difference by this. Then so let me erase first. Okay, so the capacitance will be equal to charge Q over I will replace this by this. Self-charge, distance over area, permittivity of free space, we can cancel. We charge. So C equals the permittivity of free space times area over distance between them. So this is how you compute the capacitance. The permittivity of free space, which is constant, times the area over the distance between these two plates. So as you can see in the equation of capacitance, capacitance is directly proportional to the area of either of these two plates, but inversely proportional. So again, the capacitance is directly proportional to the area. It means the wider the plate, the greater the capacitance. And then distance is inversely proportional, or distance between two plates is inversely proportional to the capacitance. It means as you increase the distance between two plates, there is decrease of capacitance. Now, no matter how I increase or decrease the potential difference between them, no matter I increase the charge density of these two plates, the capacitance is still the same, which is 0.3 picofarad. So what determines, what are the factors can affect the capacitance of a capacitor? So what if we're going to increase from the equation C equals the permittivity of free space area over distance of these two plates, right? So capacitance is directly proportional to the area, but inversely proportional to the distance between these two plates. So again, the capacitance is directly proportional to the area, but inversely proportional to the distance between two plates. Now, let us prove using this simulation. If I'm going to increase the area of these two plates, got what will happen? There is increase of capacitance. Alright, this increase of capacitance. Now, if I'm going to increase the distance between two plates, as you increase the distance between two plates, there is decrease of capacitance. So it means the distance of two plates is inversely proportional to the capacitance and directly proportional to the area of either of these two plates. So what are the factors affecting the capacitance of a capacitor? One is size and shape. Next is the surface area. Third is the distance between these two charge plates. And then the last one is the substance found between the two plates. Okay, can be insulator, can be good insulator, best insulator. So with insulator, it does not mean all electrons cannot flow. Okay, there are materials that are good insulator. There are also materials that are bad insulator. You say good insulator, very good insulator, the best insulator, meaning electrons, even a single electron cannot flow in that material. Okay? You say good, not best insulator, some of the electrons will flow. Not totally 100% all electrons cannot flow on that good insulator. So one of the factors affecting the capacitance of the capacitor is the substance found between the two plates. So let us test how big or how small 1 farad capacitor is, or 1 farad, the capacitance of 1 farad. So let us use that in a problem so that we can able to see how big is 1 farad or how small is 1 farad. So given a 1 farad parallel plate capacitor having a plate separation of 1 millimeter, that's the distance between two plates, 1 millimeter. So what is the area of the plates? So we will start with this equation. capacitance equals permittivity of free space times the area over distance between them. We will rearrange this equation to have equation of area. Then we have area equals capacitance times distance between two plates over permittivity of free space. So we'll replace capacitance by 1 farad multiply by 1 times 10 to negative 3 meters, which is equivalent to 1 millimeter. Over permittivity of free space, this is constant, 8.85 times 10 to negative 12. So permittivity of free space has other unit, which is farad per meter. So I'll explain later why farad per meter. So we'll compute, it's equal to 1.1 times 10 to the power of 8 meters squared. How wide is 1.1 times 10 to the power of 8 meters squared? I think that's wider than the baseball field or wider than the soccer field. Imagine having a capacitor bigger than the baseball field or wider than the capacitor whose plates are wider than the baseball field or the soccer field. It's a big joke. This corresponds to a square about 10 kilometer on a side. So though farad is the standard unit of capacitance, still it's convenient to use micro or picofarad as the unit of capacitance. When you buy a capacitor in the store, you don't say that you will buy 1 farad or 3 farads of capacitor, but rather you say 3 microfarad, 4 microfarad or 4 picofarad capacitor. Okay, so we can still use farad if we're going to solve problems. You just convert micro to farad by multiplying the magnitude by times 10 to the power of negative 6. Why permittivity of free space has also have a unit of farad per meter. Okay, so we know the equation of capacitance, which is equal to the permittivity of free space times the area of either the two plates times the distance between the two plates. So we are going to rearrange the equation and have the equation of permittivity of free space. Then we have capacitance C times distance between them times the over area. So what's the standard unit of capacitance? That is in farad F. It's the symbol of farad. And then standard unit of distance is meter. Over the standard unit of area is meter squared. So we can cancel meter. So we have farad per meter. So we have another unit of permittivity of free space, farad per meter. Let us solve sample problem on capacitance. So we have a parallel plate capacitor in vacuum. So the between two parallel plates is a vacuum, and these two plates are 5 millimeter apart. So that's the distance between two plates, and the area of each plate is 2 meters squared. A potential difference of 10 kilovolts is applied across capacitor. So we're going to compute for the capacitance, the magnitude of charge on each plate, and the magnitude of electric field in the space between them. Alright, so let's solve first for the capacitance. Letter A. You know, capacitance is the permittivity of free space times area over the distance between two plates. Permittivity of free space is constant, and that is equal to 8.85 times 10 to the power of negative 12 farad per meter times the area. It's the area given. Yeah, that's 2 meters squared, where the distance between two plates is in meter. That's 5 millimeter. So that's 5 times 10 to negative 3 meters. Alright, then we can solve for the capacitance. That is equal to 3.54, I think. You can double check using calculator. So you have 3.54 times 10 to negative 9 farad. So we have the capacitance. Next, we will determine the magnitude of charge on each plate. So the magnitude of charge in one plate is equal to the magnitude of charge in the other plate, but different charges, like one is positive, one is negative, but the magnitude is the same. You say 10 coulomb for one plate, so the other plate must have a negative 10 coulomb of charge. So B, the magnitude of charge. The definition of capacitance is the ratio of charge per voltage across two plates. Then charge is the capacitance times the voltage. Then we have already the capacitance, which is 3.54, and this is 3.54 times 10 to negative 9 farad multiplied by voltage. It's already given here, that's 10 kilovolts. 10 kilovolts is 10,000 volts. 10,000 volts, and that is approximately 3.5 times 10 to 1, 2, 3 minus negative 9 plus 1, 2, 3, 4 negative 5 coulomb. Okay, so that is the charge, the magnitude. So the first plate has a negative 3.5 times 10 to negative 5. The other plate is positive 3.5 times 10 to negative 5 coulomb. For letter C, magnitude of electric field in space between them. You know that the potential difference between the two plates is electric field between them times the distance between them. So we will rearrange the equation to have the equation of electric field, and we have potential difference over distance between them. So the potential difference is 10,000 volts, which is equivalent to 10 kilovolts, divided by distance between them, which is 5 millimeter, or 5 times 10 to negative 3. Then the electric field is 2 times 10 to 6 Newton per coulomb. That's the electric field.